Okay, we are back. This is from exam number 2. It's the fall of 2014 exam, and you have a copy of the PDF, and then you have a copy of also the solution, and now I'm making a video. Now, the best way to study is going to be try to do this on your own and make sure you have the basic skills that you need for the exam. So on this one, we have a 10 kip load that's applied to a loading ring that is attached to a spring and connected to a steel cable. The steel cable stretches to a 2 by 8 by 8 nylon block at C. The steel cable has a cross-sectional area given. Determine the vertical displacement of B. Okay, so when I pull on this, B is going to come down because of the stretch in the spring, because of the stretch in the cable, and because as we pull, we're going to be applying a shear force to this block, and we are going to get that skewed cross section coming over, and so we have that shear strain gamma, and we'll have a displacement. So if I want to know the displacement at B, it's going to come from the displacement of my spring plus the displacement of cable A to C plus my shear block. Okay, so as we always start with some sort of free body diagram from statics, or we can call it equilibrium if we want to. And this one's pretty easy. If I'm looking at my spring, so I have 10 kips pulling down, and I have a spring, okay? It has a stiffness of 20 kips per inch, and I can use statics. I can sum forces in the y direction. They equal 0. So the force in that spring is going to equal 10 kips, okay? As I look at my cable then, my cable is going to come around. So here's my spring pulling down at 10 kips. So I have to have a force in that cable A to C. Again, I can sum forces in the y direction, and the force in my cable A to C is also equal to 10 kips. Now, as I'm looking at my shear block, so we're going to kind of draw it 3 dimensions, like so. And I know that it is 8 inches tall, and it is 8 inches here at the bottom. And then I overly exaggerated, but we are 2 inches back. So as I'm looking at this shear force, okay, I'm going to have this shear force V that's coming across that has to equal the force in cable AC. And it's acting over that, the area that's on the top, which is 8 by 2. So you can see here, it's that shear force is acting like that. All of our material properties are given. So now let's start with the spring. So let's just start with that spring, okay? Over here, spring. Okay, so don't freak out and be like, oh my gosh, we haven't done spring since I don't know when, and I don't know how to do a spring, and what does all of this mean? Again, look at your units. If you look at the stiffness of a spring, it is given at 20 kips per inch. What does that mean? For every 20 kips of applied load, I get 1 inch of deformation. Okay, for every 20 kips, I get 1 inch of deformation. Well, I'm going to need inches on top. So every 1 inch of deformation comes from 20 kips of force, right? It's a ratio. For every 20 kips, I have 1 inch of deformation. So now if I look at this, I have 10 kips, okay? So I'm going to look at my units times 10 kips over just 10 kips. It's a force. These units cancel out. And I have 10 divided by 20, which is 0.5. So my delta of my spring, which is delta, I think I called that delta S for spring, equals 0.5 inches, okay? You don't have to remember a fancy equation. You don't have to remember anything. Just look at what your units are and look at what you're given. You are given these units and you're given a force. You don't have to overthink, okay? So now I need to look at the cable, okay? So let's start with the cable. I'm going to need a length. I'm going to need a length of cable because I know I know that stress equals E times strain, which is the force over the area in the cable, E times delta over original length. I can find my original length. I'm given E for steel. I know the cross-sectional area that was given, so I can calculate that delta. So the first thing I want to do is I want to figure out what is my length. Actually, we're going to need more space than that, so let's put it down here, length. Length equals, well, I have 25 inches coming up. I have 50 inches coming down. Plus I have 10 inches coming from here to here, plus 10 inches. So maybe let's take a different color so we can make sure that you see what we're doing. So I have, this is 25 inches. Right through the point coming down is 50 inches. Right here from that midpoint coming over is 10. What I need to take care of now, okay, what I need to take care of is the length that's actually coming up over the pulley. I need to get that length and then this length. Okay, so when I'm looking at that, I can see that, well, a pulley is round, so it's going to have a circumference, and I know that circumference is 2 pi r. Okay, 2 pi r. And my radius here, my radius is 2.5 inches. Okay, so I don't have a complete circle, I have half a circle, and down here I have a quarter of a circle. So I really only have 3/4 of a circle. So I can say plus 3/4 of 2 pi, 2.5 inches is my radius. And that's how I can get the length that's going through the cables, okay? Now in dynamics, we don't care about that because it is a constant. We aren't looking at the stretch. So in dynamics, if you're taking dynamics right now and you've looked at pulleys, we don't look at this as we're trying to find the relationships between our force and whatever it is that we're pulling. We don't care because we're concerned with the change in position and not necessarily the whole length of the cable. So you're in dynamics, we ignore those because they are a constant. But in here, we have to pay attention to them. So when I add this up, I get a length of 96.78 inches. Now, the next thing I have to do is, if I want to use this, I have to make sure we're in the elastic region. So I ask myself, are we elastic? Okay, if I'm using steel, my yield stress for steel is 36 KSI. So let's find the stress in our cable. Stress equals normal force over area. It equals, I can go back and look at my statics, 10 kips divided by cross-sectional area of 0.5 inches squared. And I know it's area because of my units. And so when I divide 10 divided by 0.5, okay, I get, I think 20, but we're going to just make sure, but that should be, let's see, where are we going here with my calculator? 10 divided by 0.5 equals 20. So I get 20 KSI, which is indeed less than yielding. So I can use delta equals NL over AE, and I have 10 kips. I have 96.78 inches, that's my length. I have area of 0.5 inches squared, and I'm checking my units, make sure my units are correct. And then I have 29,000 KSI. So I'm in kips, those will go away. I'm in inches, inches, so I'm left with inches. So my delta equals 0.066745498. I could go on for days, okay? So it's very, very small. Now I've got to come and take care of the strain here. So as I pull, as I apply that shear force across the top, this is going to, okay, it is going to kind of skew, kind of like when we cut bread, right? It kind of skews. And I know that this is my shear strain and my pin's not working. And I can also see that this is delta. And I know that with small strains, which if we're in the elastic, it's going to be small, so we'll check that. I don't have to say tangent gamma equals this over that and work in degrees. I can just say that gamma equals delta over 8 inches. Okay, so I need to find gamma, and I know that my shear stress equals G times shear strain. My shear stress comes from V, okay? V over cross-sectional area equals G times shear strain. My force V was 10 kips. My cross-sectional area is that 16 inches squared equals G for nylon is 150 KSI, 150 KSI, and gamma. Okay, and so when I check this, again, when I check this, I also need to make sure that we're in the elastic region. But when I check this, I'm going to get that gamma equals 4.167 times 10 to the negative 3, and that's in radians. Okay, which will be perfect if I'm in that small strain elastic region. I can just plug that number in here and multiply by 8 inches and get delta, right? So how can we check? How can we check? Well, V over A is 10 over 16. 10 divided by 16, let's look at that. 10 divided by 16, I have 10 divided by 16 equals, whoops, 10 divided by 16 equals 0.625. So the shear stress is 0.625 KSI. My allowable shear stress, my yielding shear stress is 8. So this value that I actually get is much less than 8 KSI, so I can use my small strain analysis. So I have 4.167 times 10 to the negative third radians equals delta divided by 8 inches. So I'm going to be left with units of inches. And when I calculate this out, delta from my shear block equals 0.03333 inches. Okay, so I have that delta from my shear block, I have the delta that comes from my cable, and I have delta right here from the spring. So my delta of B to B prime equals 0.5 inches plus 0.066745498 inches plus 0.03333 inches. And when I add all of those together, I get 0.600 inches. And there's my answer.